Now we are starting with 12.6 reaction mechanisms. In this section, we're going to distinguish net reactions from elementary reactions or steps, identify the molecularity of elementary reactions, write a balanced chemical equation for a process given its reaction mechanism, and derive the rate law consistent with a given reaction mechanism. So reaction mechanisms provide details of precise step-by-step processes in which a reaction occurs. For example, in the decomposition of ozone O3 becomes oxygen O2 plus an oxygen radical, and that oxygen radical reacts with O3 to form 2O2. And if you were to sum up these steps, you see the oxygen cancels on both sides, if you will, and you wind up with 2 ozone becomes 3 O2. Each step in a reaction mechanism is called an elementary reaction. All of these elementary steps sum up to yield a balanced chemical equation for the overall reaction. If you have a species that is produced in one step and then it's consumed in the next, it is called an intermediate. So the intermediates are not in the overall reaction, but they form. Generally, they form and are gone so fast you don't see them. So these elementary reaction equations show the chemical changes that are actually taking place. So they show us the bonds that are breaking or being made. And then the other thing is that the rate law for an elementary reaction can be derived directly from the balanced chemical equation that derives the reaction, or that describes the reaction, excuse me. So we're going to talk about some of these elementary reactions in the sense of molecularity. It's kind of a fun word, molecularity. It's a number of reactant species in an elementary reaction. So the first type is a unimolecular reaction, and these have a single reactant that produces one or more products. So this elementary reaction has some A forming products. These have a first order rate law, so your rate is equal to K times the concentration of A. For example, ozone O3 forming O2 plus O. This elementary reaction is unimolecular. You have ozone forming two products. You can also have it where the overall reaction is its own mechanism. So it's its own elementary reaction. In this example shown here, this is ethylene C4H8, cyclobutane forming ethylene. So cyclobutane C4H8 forming ethylene C2H4. It's the overall balanced reaction, but it also is a unimolecular elementary reaction. So the rate for this reaction here is equal to the negative change in C4H8 over delta T, and that rate reaction is equal to K times C4H8. We also have bimolecular reactions, and these are elementary reactions with two reactant species. So either some A and B forming products where each is first order. So you have first order in A, first order in B, and together you get a second order overall. So your rate equation is K times A times B. Or you have 2A going to products, which is second order in A, and the rate becomes K times A squared. You can have reactions that occur by mechanisms that have a single bimolecular elementary reaction, such as NO2 reacting with CO to form NO and CO2. You can also have it as steps, not steps, in a multi-step reaction mechanism. For instance, the second step in the ozone reaction, where you have an oxygen radical reacting with O3 to form two O2s. And this is also showing now the mechanism, probable mechanism between NO2 and CO to make NO and CO2. So it shows you what this transition state might be and then your products. There are such things as termolecular reactions, and these have a simultaneous collision of three atoms, molecules, or ions. These are really, really rare. Because you literally have to have three things colliding at the same time in the same in the right orientation. Everything has to be perfect for this, but it does happen. For instance, two molecules of NO can react with one O2 to form two NO2s. And notice it is a third order overall, second order in NO, first order in O2. Also happens when NO reacts with Cl2 in the atmosphere to form NOCl. Again, third order overall, second order in NO, first order in Cl. Now, when it comes to looking at these reaction mechanisms and rate laws, one step in that mechanism tends to be much, much slower than the other steps. And this limits the overall rate at which the reaction occurs and is called the rate limiting step. So if you think about it, if you were, when I was in junior high, we all had to run the mile. Pretty sure everyone had to run the mile, right? We had to do it once a week. Worst day of my life, every week. And once you were done running the mile, you couldn't do anything. You just kind of stood around until everybody else was done running, because the teachers, maybe they'd let you go change, but it really depended on the teacher. So that person that might have been the slowest would be your rate limiting step for getting to go and do other activities. That person was generally me. Another example, not using me, is cattle chutes. So, trying to herd cattle, and if they can only go through a gate thing one at a time, the slower cow, if there's one that takes the longest, is really what's going to determine how long it takes to get them all through the chute. Another place this is seen is with the reaction of NO2 and carbon monoxide. When the temperatures are above 225 degrees Celsius, our rate law is K times NO2 times CO, which is consistent with the single-step bimolecular mechanism. But when our temperatures are below 225 degrees, the rate law changes, and the rate is equal to K times NO2 squared. So this is not consistent with a single-step mechanism, but it is consistent with a two-step mechanism, where the slow step is the first one. NO2 and NO2 react to form NO3 and NO, and that NO3 reacts with CO to give NO2 and CO2. And if you were to add these up, you would see that the NO3s cancel and one NO2 cancels on each side, and we get NO2 plus CO becomes NO plus CO2. So this rate determining step, or RDS, gives the rate law showing a second order dependence on the NO2 concentration. And again, the sum of the equations gives us that same net overall equation. One thing to remember, so we've talked in, I want to say chapter 10 or 11 last semester about reversible reactions. They are at equilibrium when the rates of the forward and the reverse processes are equal. So that's good old equilibrium. It's going back and forth doing its thing. So for instance, if we have NO and NO reacting with each other, they can form N2O5. And this is actually a very important atmospheric process. Fun fact. So at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. And we could write two separate rate equations. So the forward reaction, say, is K1 times NO squared, and the reverse reaction is K negative 1, or K reverse, N2O2. Now, in general, N2O5 we can consider an intermediate, okay? It's very unstable. Sorry, that shouldn't be N2O, that should be N2O5, not N2O2. And it actually tends to only form at night, if I remember right. It's been a little while. Don't quote me there. But it's very, very unstable. So if we wanted to figure out like stuff with the rate equation, we generally can't watch the concentration of N2O5. We may be at equilibrium, but it's hard to detect. So we want to rearrange these equations to get it so that the concentration of the intermediate, in this case N2O5, is by itself and is being written now in terms of NO and the K's. So the constants are fine to leave. So when we do that, we divide both sides by K minus 1, and so we get that the concentration of N2O5 is equal to K1 times NO squared over K minus 1, K reverse. And that is not a negative K. Okay, it's just saying the K for the reverse reaction. And I know that doesn't make much sense, so we're going to actually look at an example and hopefully this will help. So we're told we have a two-step mechanism for a reaction between nitrogen monoxide and molecular chlorine. And we want to use it to figure out the equation and predicted rate law of the overall reaction. So the first thing we need to do is write our overall all of our rate laws. So step one, which is our fast step, is at equilibrium. That means we have two rates there. So we have a rate 1. I'm just going to put it as R1. No use in continue to write rate 1. And so that is going to be K1 times the concentration of NO times Cl2. Okay. And then we're going to do this for the reverse reaction. Call this R minus 1, and that's K minus 1 times NoCl2. And then our third rate, which is K, well, we'll call that R2 actually, because that's from step 2. R2, which is K2 times NoCl2. Times NO. Sorry, forgot about NO there. All right, so now we have these three rate laws. So we're going to go ahead now and try to rewrite things. We want to get rid of this NoCl2 because that's our intermediate. Okay, that's going away. You can see it being consumed in the slow step. So we want to get rid of NoCl2. And we know that at equilibrium, the rate of the R1 is equal to R minus 1. So that tells us that we can say we have K1 times NO times Cl2 is equal to K reverse times NoCl2. So now we can rewrite the concentration of NoCl2 as K1 times NO times Cl2 over NoCl2, or sorry, not over NO2, over K reverse. Okay. So now we have an expression that we can put in for NoCl2 in reaction 2. So that way we don't have an intermediate in our overall rate law. Because remember, the slow step is what really determines our reaction. So now substituting that in, we get that R2 equals K2 times K1 times NO times Cl2 over K reverse times NO. And the last thing is to just make this look pretty. And to do that, we can put all of our K's together. So we can say K2 times K1 over K reverse 1. All those constants can chill out. And we have NO squared times Cl2. So our overall rate, remember, is now the same as our slow step, or rate 2. There we go.